Hey, good evening, everybody. And welcome to another session of organic chemistry. Okay, in today's session, we are going to continue our discussion of the chemistry of alkenes, taking from chapter 8 of your book. Before we get the discussion started, a couple of announcements. On Monday, there will be a review session using our chapter 8, end of chapter questions in our. That is at 8 o'clock on Monday, October 15. Then on Wednesday, October 17, there will be another online review session. This time we will use the previous 1-hour exam as discussion questions for the online session. So mark your calendar for those 2 days. Of course, you know the second exam is scheduled for Thursday, October 18. Okay, so you remember when we left on Tuesday, we had a discussion on the synthesis of alkenes. And during that session, we gave you the synthesis of alkene starting from an alcohol, in which we informed you that if you take an alcohol, you will be able to dehydrate an alcohol to form a carbon-carbon double bond. So right now we want to give you another synthesis of alkene. This we call dehydrohalogenation. Dehydrohalogenation. In other words, if you take an alkyl halide, just like this compound here, which is bromocyclohexane, and you use potassium hydroxide in ethyl alcohol as solvent, you will be able to remove the bromine and the hydrogen, and that is why we call this dehydrohalogenation. And in the process, you end up forming a carbon-carbon double bond and potassium bromide and water. Of course, our focus here is the synthesis of the alkene. For example, go back? Okay. Another example of the dehydrohalogenation, if you take this bromobutane right here, in this case, you are using sodium ethoxide. The ethoxide, this is the conjugate base of ethyl alcohol. Take sodium ethoxide, also using ethyl alcohol as solvent. You will be able to perform dehydrohalogenation on this molecule to form carbon-carbon double bond. In this case, we form two types of alkene. This alkene here, this is the major product. Does anybody know why this would be the major product? And this is the minor product. Anybody has an idea why? Remember, we gave you the order of stability of alkenes. Okay, so now that becomes very important. Whenever you synthesize an alkene, the more stable alkene or the most stable alkene will be preferred in terms of this the formation of the product. So in this case, you have this product here. This is a tri-substituted alkene as opposed to a di-substituted alkene. So that is why this is the major product. Okay, and that will be the recurrent theme in all of the synthesis of alkenes. Anytime you want to synthesize an alkene, if there is a possibility of making or producing more than one type of alkene, the more stable or the most stable alkenes will be formed. Yeah, Ryan, go ahead.
Okay, so for this first dehydrogenation, okay, I understand. I'm confused where like that's dehydrogenation.
Okay, what I want you to take away from this is that whenever you have a bromoalkane, okay, in this case, a bromocyclohexane, all you are going to do, you will remove the bromine and hydrogen next to the attached to the next carbon atom. Okay, so these two will be removed, and in the process, you are going to form a carbon-carbon double bond here, and that is what happens here. Okay, the mechanism, I do not want to go over the mechanism now, but that is in your book, and it's also in the PowerPoint lecture material that are posted in Blackboard. Okay, but what you need to take away from there is that whenever you have an alkyl halide, the bromine and the hydrogen will be removed, and between them you have the carbon-carbon double bond. And that is what you have here. You remove this bromine here, you remove an hydrogen here, and you form a carbon-carbon double bond right here. The same thing on this side. You remove this bromine, you remove this hydrogen, and you form a carbon-carbon double bond right here. Okay. Somebody has a question in the back? Oh, okay. Okay, so now let us give you a couple more examples of dehydrohalogenation. Okay, dehydrohalogenation simply means you are removing hydrogen and an halogen. The halogen could be bromine or it could be chlorine. Say, for example, if I have this here, notice that we have hydrogen here and hydrogen here. And I give you this reagent. Let us use the ethoxide. Of course, in ethyl alcohol. Okay, what do you think the product will be? How many different types of product do you expect here? Okay, let me number the carbons. Let us say this is carbon 1, 2, 3, 4, 5, and 6, and say this is carbon 7. Okay, where do you expect the carbon-carbon double bond to be? 1 and 6? Okay, very good. So you expect 1 and 6? Because you remove this hydrogen and the bromine, right? So you form a carbon-carbon double bond right here. And then this is here. And the other hydrogen is still here. Okay, what other product do you expect? 1 and... Okay, you form you form the KBr. But for the most part, we are interested in the organic product. Okay, so what else? I'm sorry, sodium borate. Sodium bromide. Okay, now for the most part, we are interested in the organic product. So what other organic product do you expect here? Where the double bond will be? Which one? 1 and, well, that would be the same product as 1 and 6. It will be the same product as 1 and 6. It will be this. If you name these two compounds, they will be the same. Okay? Okay, so that is the same. Okay, what other product do you expect? 1 and, exactly, 1 and 7. 1 and 7. Okay, so we expect a carbon-carbon double bond between 1 and 7, because you could remove one hydrogen here and the bromine here, and then you form the carbon-carbon double bond here. So therefore you get 1 and 7. Okay, now, supposing I ask you, which is the major product here? Let us say this is compound A and compound B. Which is the major product? A. Why? That is correct by the way it's supposed to be A. That's the major product, and this is the minor product. Why? Because it is more substituted and therefore more stable, right? Very good. Okay, so I think you guys got the idea. Now, okay, now let us go to, yes. Sodium methoxide, that is sodium methoxide. Okay, go ahead.
Everything else is not sodium dissolved or product.
The sodium dissolved?
No.
Say that again.
All right, the CO2, K2, the sodium, everything but the sodium dissolved as you go to the product.
Okay. Wait.
Yeah.
What happened to what?
Everything else dissolved besides the sodium.
Okay, what else do you do?
What you're saying is, you just skipped over CH3 to what happened to it. Well, you already said
in the ethanol?
Yeah.
That is the solvent. Okay. The ethanol is the solvent. Okay, in most of these reactions, sometimes we may not show you the solvent. But when you go in the laboratory, you have to use a solvent in order for the reactants to mix together, yes. The hydroxide is also performing a function here. But, okay, we do not want to go into the mechanism right now. I'm simply saying that whenever you see this reagent here, the ethoxide and ethanol, and then you see an alkyl bromide, what this reagent will do is to remove a bromine and an hydrogen from the alkyl bromide to give you an alkene. Okay? Yes.
Okay, so this is just when you, from that first step, you remove the hydrogen and the bromine. Why can't I can still do the major part of that cycloalkyl structure plus NADR plus H2O?
Mm-hmm.
So same
no, well, no, you do not get H2O here. What you're going to get will be alcohol.
But if you add the OH,
that would be H2O. Yeah, right. Okay, in other words, if you did this, supposing we did this, supposing we have this, and in this case, instead of using the ethoxide, we use potassium hydroxide. Okay, the hydroxide is the conjugate base of water. Okay, and then we use our ethanol as solvent. Okay, okay, this is ethanol right here. Okay, okay, we use ethanol as solvent. Okay, so what product do you expect to get here? The organic product. Okay, let me label this. Let me label this. Let's say this. Let us say this is carbon 1, 2, 3, and 4. Okay, what product do you expect? Where would the double bond be?
Is it a bromine?
Yeah, this is a bromine.
Okay, so it'll be between 2 and 3.
Between 2 and 3? So you get between 2 and 3. So you get carbon-carbon double bond between 2 and 3. And okay, any other product?
Yeah.
Yes. Between which one? 2 and
We'll make that 5.
no, this is 1. This is carbon 1.
You know, the decision went through that branch.
This here?
You make that carbon 5, and you don't follow through.
Where does it? Okay, it's the same as being here. I'm sorry. It's the same as being 1. Okay. Between 1 and 2? Okay. So you could also get this product here. Okay. And which will be the major product? A. We call this A, and we call this B. So this is the major product. Okay, can anybody tell us why this should be the major product? Because this is a more substituted alkene than this one here. This is a di-substituted alkene, and this is a tri-substituted alkene. Okay? So therefore, this will be more stable, and as such, it will be the major product. Okay. If you look at this, the question is, how do I know whether these are the substitution of a particular alkene? This molecule here, say this is non-substituted. Alkene, because you have hydrogen attached to all of those carbon of the carbon-carbon double bond. Okay, you follow that? Okay, now, supposing I take one of the hydrogen out, I replace with an alkyl group, right? Okay, what kind of substitution is that alkene? What kind of substitution is it? We say that is mono-substituted. Okay? Supposing I remove another hydrogen, I replace with another alkyl group. What kind of substitution is that? We say that's a di-substituted. So you could replace all of the hydrogen, then you become tetra-substituted. You replace one of the 3 of the hydrogen, become tri-substituted. That is what we have here. This is a tri-substituted, and this is a di-substituted. Okay? Okay, so now let us move on. Okay, go ahead. Okay, why don't you see me in the office tomorrow? Okay. Okay, now, let us now begin to take a look at these reactions of alkenes. For the reactions of alkenes, I am going to give you a series of reactions. Some of them, of course, I will give you the reaction mechanism. For the most part, I will not have to give you the reaction mechanism. All you need to know is what reagents will perform a particular synthesis. Okay, so If you recall, at the beginning of this chapter, we told you that the carbon-carbon double bond is very central to the chemistry of inorganic chemistry with regard to synthesis of different types of classes of compounds. Take a look at this carbon-carbon double bond here, an alkene. By the time we finish this chapter, you should be able to go from this alkene to what we call a diol, 1,2 diol, in which you add 2 hydroxyl group across the carbon-carbon double bond to form this molecule here. You also should be able to take an alkene and form carbonyl compounds. You also should be able to take an alkene and form a cyclopropane molecule. In other words, we will be giving you the reagents that will enable you to perform these operations. Also, you should be able to perform a reaction in which you form what we call the epoxide. Notice what we've done here. We are adding oxygen across the carbon-carbon double bond. Also, we will give you a reagent. By now, you should know how to do this. We've already given you this to form an halide. Also, we'll give you a reagent that will allow you to form what we call a dihalide. Another reagent that will allow you to make what we call halohydrin. You notice for the halohydrin, you have a molecule in which you have the hydroxide and an halogen on adjacent carbon atom. What do you mean by that? Carbon atom next to each other. And that is what we call halohydrin. Of course, we will also give you reagent that will allow you to make alcohol from alkenes. And finally, you also know how to make alkane from an alkene by adding 2 hydrogen atoms across the carbon-carbon double bond. I believe this we've done already, and also this we have done already. Okay, so let us start with these different type of reactions. Okay, let us start. I'm going to put numbers on them, so just follow me with these numbers. Let's start with the addition of hydrogen halide. This is all reactions of alkenes, under reactions of alkenes. Addition of hydrogen halide. For the most part, the addition of hydrogen halide that is of interest to us will be adding hydrogen bromide or hydrogen chloride across the carbon-carbon double bond. I believe we've done a lot of this already, so I will simply give you a couple more examples. For example, if we have this molecule here, and we have either hydrogen bromide or hydrogen chloride, we will add the hydrogen and bromine across the carbon-carbon double bond. Does anybody know where the hydrogen will go? Okay, why? Anybody know why? That is correct. The hydrogen goes here. Okay, exactly. This is a mechanical addition, right? In which, in the mechanical addition, the hydrogen goes to the carbon that is attached to more hydrogen. Okay, and the bromine goes to the carbon that is attached to less number of hydrogen. So here, this carbon has no hydrogen, and this carbon has 1 hydrogen. So therefore, this hydrogen comes here, and the bromine goes here. And that is why you have this product. Now, this type of reaction, we say this is a regiospecific reaction. Regiospecific because those atoms that are added, they are added to specific position on the carbon-carbon double bond. In other words, the hydrogen will come here and the bromine will go here. Okay? And of course, this is an example of Markovnikov addition. And I believe we gave you the mechanism of this last week, so we don't need to do that again. But the fundamental reason why Markovnikov addition works, what is the fundamental reason for the Markovnikov addition? Why does it work? Anybody? Because it forms more stable, it forms more stable intermediate carbocation. During the process of the reaction, you form the more stable intermediate carbocation. And that is the fundamental reason why Markovnikov rule works. Okay. We also have, call this reaction 2, hydrogenation. Catalytic hydrogenation. In the catalytic hydrogenation, what are we doing? We are adding the elements of hydrogen, 2 hydrogen atoms across the carbon-carbon double bond using a catalyst. Once again, we use this same example here. Say we use this molecule here. And we have hydrogen using either platinum as catalyst or nickel as catalyst or palladium or sometimes platinum oxide. All of this could be used as catalyst with hydrogen. And then the product you get is now you see the stereochemistry that we show here. This is a stereospecific reaction because all you get is the cis product. So this is the cis product. Therefore, we say this reaction is stereospecific. Stereospecific because we only get one type of stereoisomer. We do not get the trans isomer. Yes.
Does it matter which are coming at you or which are...
No, it doesn't. As long as it is cis, right? Okay. So this is an example of catalytic hydrogenation in which we are adding 2 hydrogen atoms across the carbon-carbon double bond. Okay, 3. Halogenation. This is addition. Addition of two halogen atoms across the carbon-carbon double bond. And specifically, the halogen atom that is of interest to us would be bromine and chlorine. Okay, so in this case, supposing we have this, and if we have bromine, the same thing will apply to chlorine, we get this product. Now, once again, you see what the product we obtain here. We obtain the trans addition product. In other words, the two bromine atoms are added across the carbon-carbon double bond such that you have one bromine is on one side of the ring or one side of the molecule, and the other bromine is on the other side of the molecule. In other words, they will be trans to each other. Okay? So we also say this is a stereospecific reaction. Okay. For this particular reaction, I would like to give you the mechanism for this reaction because it is very important. Do you have a question? See, you have a question? Oh no. Yeah, go ahead. Number what? I can't hear you. Okay, the one I did before said this here. Why is it 6? Okay. What happens? You are using a catalyst. Okay. Essentially, you are asking for the mechanism here. You are using a catalyst, and the catalyst is flat. You know, the platinum, palladium, and all that. And what happens? The hydrogen is sticking out. Okay, and then the carbon-carbon double bond is simply moving along the surface of the catalyst. And so therefore, the only possible way in which those hydrogen will be added to the double bond is on one side of the molecule. Okay. Okay. Anyway, so let us give you the mechanism for this bromination reaction, and the same mechanism will apply to chlorination reaction. Because we do need to explain why we got the trans product. Okay, so we start off with, keep in mind our focus in all of this reaction is the carbon-carbon double bond. And so you are, the bromine molecule moves as close to the carbon-carbon double bond as much as possible. In so doing, because you have 5 electrons here, and you have a bunch of electrons around this bromine here, also here, there's what we call a temporary dipole. in which the electron flow will simply move away from this side. And as a result, what you get is this pi electron here will now act as a nucleophile to attack this bromine here, which at this point will be almost like a temporary dipole is set up with a temporary positive charge to it. And as such, you have this pi electron comes here, attacks this bromine, because the bromine now, this bromine will be acting as an electrophile. And as such, you are going to break this bromine-bromine bond. Now, what is also happening, just as, let me make this a little bigger so we can see it. I'm going to write the same structure, but it's going to be bigger, so you don't need to erase what you have. I will say these are the temporary dipole in which you have this become partial positive charge on this bromine, partial negative charge on this, and as such, the pi electron here comes here, attack this. Think of a situation in which that pi electron is attacking using these carbons here, and at the same time, you are going to be developing a positive charge on this carbon here. And this electron here simply come here, attack this carbon. And what do we get? You form what we call a bromonium ion. And a positive charge on, because the bromine is using a pair of electrons to bond to this other carbon here. And of course, we also have the bromide is formed. Okay? So now we form what we call a bromonium ion. Okay. Now, once you form that bromonium ion, think of the bromonium ion as this here. Okay, just okay, think of the bromonium ion as this, in which you have the bromine. Oh. Okay, the bromine is here, right? Now, what is going to happen? This bromide here, you notice the bromide here, this here, could now attack this molecule either from here, from the opposite side where the bromine is. The bromine is here. So now the bromide that is formed, the ion that is formed, who attack this from here? If it attacks, the bromine will open up. Or it will attack from here. If it attacks, the bromine will open in the other direction. And that is how you end up getting the trans isomer. Okay? So now you have, so I'm going to give you two attacks. Supposing we have the attack on this side. if we attack from this side or from this side, okay, keep in mind the bromine is on top, so this bromide ion is coming from the back. Okay, and let us call this attack A, and this call this attack B. Okay. Okay, so what is the product for A? If we attack A, gives us this product. Okay, keep in mind once the bromine attacks from the back here, pushes the hydrogen up. So the hydrogen now is going to be here, and the bromine is here. Hydrogen is here. That means that the bromine comes up, so now the bromine will now be here, and of course the hydrogen is here. That is one product based on attack from this carbon from the back. Supposing now we have the attack from the B. Attack from B, what do we get? Okay, it's coming from the back, so it pushes the hydrogen up, and the bromine is here, and therefore, keep in mind once it attacks this will open up here. This will open up to here, and when this attacks this will also open up to here. Okay, so we have so you see why this particular reaction gives us the trans isomer, and that is because of the formation of this intermediate bromonium ion. Because the incoming bromide this here has no other alternative but to attack from the back of the molecule. It has to attack from here, and once it attacks from here, the bromine will open up. So it has to be opposite to each other. Okay, and that is why we have the trans product. Also, another thing that you need to be aware of, if you look at these two molecules here, attack from here, say this is A, and this is B. Both of those are mirror images of each other, and they do not superimpose on each other. Okay? So what do you call those two, A and B? Enantiomers. These are enantiomers. Okay, how do we know that this is the reaction mechanism? Because we could use the optical, determine the optical activity of the reaction mixture. And what do you think happens if we determine the optical activity of the reaction mixture? What do we get? What will be the optical activity of this reaction mixture? Will it be the reaction mixture be optically active or optically inactive? Inactive. Why? Because they cancel each other out. Even though each one of the products, A and B, each one of them is a chiral molecule, the pure enantiomer by themselves who have optical activity, but the product that you get will be optically inactive. And that is one of the ways in which we are able to determine the mechanism of this reaction. Because we have to be able to explain how do we get an optically inactive mixture from this particular reaction. And we also know that the product is a trans product. Okay, so this is the mechanism that we are going to come back during I'll come back to revisit this mechanism during the course of this chapter. Okay, so anyway, at this point we have given you the mechanism for the bromination or the same thing happens with chlorination of alkane. In the case of chlorine, the intermediate will be called chloronium ion. Okay? Okay, so let us give you one more example. Supposing we have this. Supposing we have this compound, and also you also get the mirror image of this here. Okay? You got that? Okay. What happens? Don't forget you form the bromonium ion here. Once you form the bromonium ion, the other bromide will come in, attack this, and that is how this goes up here. So you form the bromonium ion, carbon, carbon. Okay. And then you have this here. Hydrogen here. And here you have hydrogen here. Okay, now this other bromide comes in. Okay, keep in mind that this comes in here, and this here. This other bromide comes in to attack from here. If it attacks from here, and this opens up, and therefore you get this. Okay, and you could also give the same a similar justification for attacking on this side to form the mirror image of this. Okay. Okay, so that is the bromination or halogenation reaction. Was that reaction number 2 or 3? Yes. Because that we know from experiment. That's what we get. So there are many ways in which we could determine this the structure of these molecules. So what we are simply showing you, these are experimental results. Okay, so we do know that it is a trans product. Okay, so reaction number 4, still under reactions of alkenes. Now let us now begin to take a look at addition of water. Okay, no, I want to do the addition of hypo Halous acid. Hypohalous acid will be this here, bromine attached to hydroxide, or chlorine attached to hydroxide. We could also have the hypohalous acid, any one of these here, adding to a carbon-carbon double bond. Generally, in order to generate this hypohalous acid, you will need bromine in water or chlorine in water. Okay. So, for example, if you have this molecule here, just as we had before, you have bromine, water. Now, this reaction also gives you a trans product, because what happens, the first thing that happens is the formation of the bromonium ion, just as we gave you before. And so you form this product here. So here, by using bromine water or chlorine water, we are able to add bromine or chlorine and hydroxide across the carbon-carbon double bond. And this type of molecule is what we refer to as halohydrin. Halohydrin, as you can see here, the addition of the hypohalous acid across the carbon-carbon double bond also gives you a trans product. Trans addition product. Okay, this is also an example of a stereospecific addition reaction. Okay, that's number 4. Number 5. Okay, addition of water. Addition of water across the carbon-carbon carbon-carbon double bond. In this case, water by itself does not add to carbon-carbon double bond, so we have to use either some acid catalyst or some special reagents. So under the addition of water, let me say A, acid catalyzed, hydration of water, or hydration of alkene. Whenever you add the water across the carbon-carbon double bond, we say we are doing hydration. So in this case, we take the carbon-carbon double bond, and if we take this, and here we could use any dilute acid, we could use sulfuric acid, or phosphoric acid, all in water. Whenever you have the phosphoric acid or sulfuric acid in water, you will form hydronium ion. So you could also say hydronium ion. Okay. When you do that, what you will get? You get addition of the elements of water across the carbon-carbon double bond in a mechanical fashion. In a mechanical fashion. So, where will the hydrogen go? In a mechanical fashion. The bottom, exactly. So you get this product here. Because what are we doing? We are essentially adding the element of water, this here, and this here, across the carbon-carbon double bond. Using acid catalysis. Water by itself will not do it. Okay? You want the mechanism for that? You got enough mechanism by now, right? Okay, so let's move on. Now, there are some other ways in which you also, actually that mechanism is very important. Let me give it. Now, let us give the mechanism of the acid catalyzed hydration, because it is very important. mechanism of acid catalyzed hydration of alkenes. Okay. The first thing that happens you have the proton from the acid. Let us use the hydronium ion. What do you think the first thing that will happen? What do you think the first thing that will happen? I will give you a guess. It is the reverse of dehydration. Okay, what is the first thing that happens? You have the pi electron and the proton here from the acid. What will happen? What acid-base reaction? Nucleophile. This will act as a nucleophile and this will act as electrophile, right? Okay. Comes in here. And of course, since this will be a Markovnikov type reaction, you form the more stable carbocation. That is the reason I wanted to show you this mechanism, because this particular reaction goes through the formation of a carbocation. So you now have this. Keep in mind you have hydrogen here to start with. Of course, plus we also form, keep in mind that we also form water here. So now you form this tertiary carbocation at this point. Now the reason I want to show you this mechanism, because the acid catalyzed hydration of alkenes, since it forms carbocation, it is prone to rearrangement. Okay? The carbocation is prone to rearrangement. So at this point, the water that is formed come here, attack this. Keep in mind you also have water in the system. Okay, attack that, and then what do we get? And so we end up with a protonated alcohol. So that is why we told you this is the reverse of dehydration. And at this point, another molecule of water comes in. Abstract or will remove or pick up the proton from the protonated alcohol, and then you release the proton, and then what do we get? So the net process, if you notice here, the net process is the addition of water across the carbon-carbon double bond. Okay, notice that we regenerate the hydronium ion. So the hydronium ion that we started with here was simply just being used as a catalyst. Okay, the net process is the addition of this water here across the carbon-carbon double bond. Now I bring this up because this particular method for making alcohol could be problematic, because you are forming the intermediate carbocation that is prone to rearrangement. Now, if on the other hand, you want to form an alcohol by adding water to carbon-carbon double bond without the formation of a carbocation, there are a couple of reagents that you can use. Okay, so let us say this is 5B, addition of water by hydroboration/oxidation. Now in this case, you take a carbon-carbon double bond, take this here, and you use this molecule here. We say step 1, borane. This is borane. Our molecule is called borane. You react borane with a carbon-carbon double bond. And then step 2, you then add hydrogen peroxide in basic medium, sodium hydroxide or potassium hydroxide. Now keep in mind, what we want to do here is to add the elements of water across the carbon-carbon double bond. But in this case, what is this one here? Okay, in this case, what do we get? We get this product. Now we're going to get a product that is what we call an anti-Markovnikov product. Okay, ordinarily, where do you expect the hydrogen to go in a Markovnikov addition? It comes here, right? Now, when you use this reagent, this is a very important reagent. This will give you addition of water, elements of water across the carbon-carbon double bond in an anti-Markovnikov fashion. In other words, here, actually, let us show the stereochemistry here. In other words, we have hydroxide here. Keep in mind, we add hydrogen here to start with. That is that hydrogen. And then the other hydrogen that is added. So show this here. The other hydrogen that is added, will be here. Okay? So what do we have here? So what do we have here? Those two hydrogen, the hydrogen and the hydroxide, how did they get added to the carbon-carbon double bond? From the same side. From the same side. So therefore, this particular reaction, not only it is an anti-Markovnikov addition, this anti-Markovnikov addition addition of water it is also what we call a stereospecific reaction, because we get also a stereospecific reaction. Okay? Because what we get here is a cis addition product. So this product here is a cis addition product. Cis. Okay. So if you want to get this an anti-Markovnikov addition, what reagent do you need to use to add water to carbon-carbon double bond? Borane followed by hydrogen peroxide. Yes. Oh, because this hydrogen and the hydroxide were added across the carbon-carbon double bond on the same side of the double bond, and that is why it is cis. You see the stereochemistry here. This is the hydrogen that was added, and this is the hydroxide that was added on the same side, and that is why we say cis. Okay, but more importantly, this is what we call an anti-Markovnikov addition of water across the carbon-carbon double bond. Huh? Okay, a few more reactions before we stop. A few. Now, supposing we want to add water across the carbon-carbon double bond in a Markovnikov fashion without having to form a carbocation. Okay, so we could do that also. So this would be, I believe this is 6. It is 6 and 5C. Okay, addition. Is it 5C? No. Addition of water by mercuration, demercuration. Okay, what is that? Very good question. Now, for this we use mercury acetate. The reagent that we use here is mercury acetate. If you have using the same molecule here, then we use mercury acetate okay, for this here, instead of writing this here, what I've just written there, you could just do this, OAC, okay? For this here, you could just say OAC, okay? Yeah. Yes. That is this molecule here. It's the shortened form of this here. The AC stands for acetyl. Okay, and the O is the oxygen. Okay, so this will be step 1, and you follow that up with sodium borohydride. This will be a Markovnikov addition of water across the carbon-carbon double bond without going through the formation of a carbocation. So this would be this here. Okay, this reaction is regiospecific, just like all Markovnikov addition reactions. Markovnikov addition. I'm sorry, no, got it right. You guys did not correct me. It should be here. It's a Markovnikov addition. Okay? The hydrogen goes here, the hydroxide goes here. So this is a Markovnikov addition. So therefore, we have given you 3 different ways of adding water across the carbon-carbon double bond. What are those 3 different ways? Borane, hydroboration, oxidation, right? acid catalyzed addition of water, and finally the demercuration. Okay, mercury acetate followed by sodium borohydride. This is called, we call the sodium borohydride. Sodium borohydride. Okay, just a couple more reactions. Okay, couple more reactions. Now, before we leave, and a couple more and then we'll leave. I know you guys are tired. Okay, 6. Huh? This is the depth we're going to go through. This is the depth that we're going to. Okay, so 6. We're going to do review on Monday, Sunday night, oh yes? You want my wife to leave, you want my wife to divorce me, right? Okay, no, we cannot do it on Sunday, we do it on Monday, review on Sunday, on Monday. I have to go to church on Sunday. Right? Don't you guys have to go to church? I go to church at night, all day. I go to church all day. Okay, now you guys want to waste, take my time. Let us do one more. Let us do one more. Oxidative cleavage of carbon-carbon double bond. Okay, now with the oxidative cleavage, now stay with me now, this is very important. Try to stay with me now, okay? Supposing we take this molecule here, and I have step 1, ozone, and then I follow that up with zinc in the presence of acetic acid. See what is going to happen? We are going to split this carbon-carbon double bond so that each carbon of the carbon-carbon double bond becomes a carbonyl group. So now we form 2 products. Plus okay. In this case, we form these 2 products. They happen to be the same product because we are starting with a symmetrical alkane. Now, supposing we are starting with this type of alkane, and we use the same reagents, zinc, followed by OAC. I told you OAC for the, okay, that's acetic acid. Okay? Now, what do you think we're going to get? We split this here. This reagent here, what it does is to split the carbon-carbon double bond so that it becomes a carbonyl group. So now we form this product and this product plus this here and this here. Okay. Now supposing no. Oh, want me to go back? Okay, I'm sorry. Okay. No, one more reaction now, then we leave. No. What? Okay, so now, but one more reaction. Supposing you have this. Yes. Now, the reaction I've just given you now is called ozonolysis. The reaction with ozone with carbon-carbon double bond is called ozonolysis. Now, so this is number 6. Yeah. Just give you another example. Now, supposing I give you this molecule here, and I want you to perform ozonolysis. Step 1, followed by hydrogen peroxide. Followed by zinc and acetic acid. Now, what is going to happen here? You split this here. The carbon that is attached to an hydrogen becomes the carbon of an aldehyde, the carbonyl of an aldehyde, and the carbon that has no hydrogen attached to it becomes the carbonyl of a ketone. So what do we get? Okay, you get that product. So that is the end of today's presentation. We are going to finish chapter 8 on Tuesday and then do some problems on Tuesday. And do not forget, we do have an online session on Monday. Okay, so the last set of reactions I've given you is what we call ozonolysis. And what ozonolysis does is to cleave the carbon-carbon double bond to give carbonyl compounds.